First of all, let us consider the ozone molecule. We will try to draw the Lewis structure. There are 3 oxygen atoms in ozone. Therefore, the total number of valence electrons is 18. Now let us distribute the valence electrons. We give a double bond here. Octet is fulfilled for these atoms. Now 1 electron goes here, resulting in a formal charge, +1 here on the central atom and -1 here. Now join this bond. It's okay now. Octet is now fulfilled for all the atoms, and the total charge is +1 and -1, which is 0. Now by the same procedure, we may draw another Lewis structure like this. Now the matter of fact is that neither of these structures are real. The real structure is actually an intermediate between these 2 structures. This can be understood from the fact that the oxygen-oxygen bond length in ozone is 128 picometers, which is a value intermediate between oxygen-oxygen double bond, which is 121 picometers, and oxygen-oxygen single bond, which is 148 picometers. The 2 bond lengths in the actual structure are equal. One of the double bond is a pi bond and remains both above and below the ozone molecule. Actually, this pi electron cloud seems to be dispersed like this. These Lewis structures are called contributing structures or resonance structures or canonical forms, and this is the actual structure, or better known as resonance hybrid. Therefore, the dispersion or delocalization of pi electrons or p electrons over the entire molecule, which can be represented by more than one Lewis structure, is called a resonance or mesomeric effect. The electron charge is maximum dispersed in the resonance hybrid structure. Therefore, it is the most stable and of lowest energy. The more the number of resonance structures, the more the pi electron is dispersed or delocalized, the more stable is the molecule. Example, in 4-nitroaniline, the lone pair on NH2 group is dispersed over the entire molecule like this. This is not possible in the case of 3-nitroaniline. Therefore, 4-nitroaniline is more stable and hence less basic than 3-nitroaniline. Now, in the case of ozone, the 2 resonance structures are equivalent with the same energy. In the following example, the resonance structure of phenoxide ion are shown. Structure 1 and 5 are equivalent structures. Structure 2 and 4 are also equivalent structures. But all of them together is not equivalent. Out of these multiple resonance structures, some are major contributors and some are minor contributors. The major contributors have lesser energy and resembles the resonance hybrid to a maximum extent. Now, one thing we must keep in mind, that all the structures have the same total charge and the position of the atoms remain the same in all the structures. Let us discuss some of the points that make a resonance structure the major contributor. Now, the first point is a resonance structure where all the atoms fulfill the octet of valence electron is a major contributor. whereas the resonance structure having one atom not fulfilling the octet of valence electrons is the minor contributor. Example, in carbon monoxide, we have the two structures over here. The second structure is a major contributor. Why? Because here both carbon and oxygen has octet of valence electrons. Now the first one is not so much stable because here carbon does not fulfill the octet of valence electrons. Now point number 2, a resonance form having more covalent bonds is more stable. See the resonance structures of formaldehyde. Structure 1 is more stable because it has 4 covalent bonds, whereas structure 2 has only 3. Point number 3. A resonance structure having a formal negative charge on a more electronegative atom is more stable. Example, in phenoxide ion, we have these two structures. The structure 2 is less stable than structure 1 because in structure 1 the formal negative charge is on oxygen, which is more electronegative than carbon. Now point number 4. The resonance structure that does not have a charge separation is more stable. Let us draw the resonance structures of aniline. The two structures are like this. Structure 1 is more stable because structure 2 has a charge separation and is a dipolar resonance form. Now point number 5. In dipolar resonance forms, more the charge separation, more stable is the resonance form. Let us draw another structure of aniline like this. In this structure, the charge separation is more and hence it is more stable. Resonance energy. Now out of the 5 structures of phenoxide ion, structure 1 and 5 are the major contributors and have the minimum energy. The difference in energy of this structure and the resonance hybrid is equal to the resonance energy of phenoxide ion. Therefore, resonance energy can be defined as the difference of energy of the resonance hybrid with the most stable canonical form. Plus R or plus M effect and minus R or minus M effect. When a substituent of a conjugated system increases the electron density in the entire molecule by delocalization mechanism, it is called plus R or plus M effect. The OH group, OR group, SH group, NH2 group and R2 groups fall under this category. The mechanism is like this. When a substituent of a conjugated system decreases the electron density on the entire molecule by delocalization mechanism, it is called minus M or minus R effect. Substituent groups like NO2, carbonyl group, cyanide group, carboxylic group, SO3H group fall under this category. The mechanism is like this. Resonance effect versus inductive effect. Groups like hydroxyl amino have plus R effect as well as minus I effect, but in phenol and aniline the plus R effect outweighs the minus I effect. This is the reason why phenol and aniline is more reactive towards electrophilic substitution than benzene. However, in the case of halo groups, the inductive effect is more stronger and halobenzenes are less reactive towards electrophilic substitution than benzene. However, halobenzene are orthopara directing due to plus R effect.